There is a sandstone plateau less than 2 hours from the center of Sydney that most Australians have visited and almost none of them understand. They have stood at Echo Point and looked out at the Three Sisters. They have taken the scenic railway down into the Jameson Valley and walked part of the Prince Henry Cliff Walk. They have driven through Katoomba and Leura and bought a scone at a tea room and driven back to Sydney thinking they have seen the Blue Mountains. What they saw was the surface. The surface is remarkable enough. Sheer sandstone cliffs dropping into deep forested valleys. The blue haze that gives the mountains their name drifting across the valley systems in the morning light, produced by the volatile oils released by the eucalyptus forest covering the plateau. Waterfalls dropping hundreds of meters from the cliff tops into the gorges below. A landscape that is dramatic and beautiful and immediately accessible from the largest city in Australia in a way that no comparable landscape anywhere else in the developed world manages. But the surface is only the beginning of what the Blue Mountains are. Because when scientists looked at this plateau not as a scenic day trip destination but as a geological system, a biological archive, an archaeological record, and a structure with deep physical properties that laboratory instruments have only recently been able to measure, what they found revised the understanding of multiple disciplines simultaneously. A living species believed extinct for 2 million years. A geothermal system operating silently beneath one of Australia's most visited landscapes. A biological record in the deep canyon systems that is still being assembled. And an archaeological record of human presence extending back to the founding of this continent's human story. None of that is on the signage at Echo Point. This is what the research has found. If you are new here, this channel covers Australian history, science, and country that most people were never properly taught. Subscribe now and let me know in the comments below how many times you have been to the Blue Mountains and what you actually did when you were there. Let us start from the beginning. Because understanding what the Blue Mountains actually are geologically is the foundation of everything else that has been found here. The plateau is made of sandstone. Specifically the Hawkesbury Sandstone and associated formations of the Sydney Basin, sedimentary rock deposited when this part of eastern Australia sat at the bottom of a shallow sea and river system approximately 230 to 300 million years ago during the Triassic and Permian periods. The sediment accumulated in layers on the ancient seafloor and riverbed, grain by grain, over tens of millions of years, compressed under its own weight into the hard sandstone that now forms the visible fabric of the plateau. That sandstone, and the coal measures and other sedimentary formations that underlie it in the deeper parts of the Sydney Basin sequence, are sitting on top of a geological basement of much older and harder crystalline rock, granite and metamorphic rock formed during earlier episodes of geological activity that predate the sandstone by hundreds of millions of years. This layered geological architecture, young sedimentary rock above ancient crystalline basement, has two consequences that are important for understanding everything else that has been found in this landscape. The first consequence is the topography. Sandstone is hard enough to form vertical cliffs where the plateau edge has been undermined by erosion of the softer layers below it, but it is also porous and subject to chemical weathering by acidic groundwater. The canyon systems of the Blue Mountains were carved by rivers cutting downward through the sandstone over millions of years, exploiting weaknesses in the rock along joints and bedding planes. The speed and depth of the canyon cutting depended on the hardness of the specific sandstone layers encountered at each depth, producing the characteristic step topography of the Blue Mountains valleys where harder and softer layers alternate in the cliff profiles. The second consequence is the thermal environment. The ancient granite and metamorphic basement beneath the sandstone contains elevated concentrations of heat-producing radioactive elements, uranium, thorium, and potassium, that generate heat as they decay. The thick sandstone sequence above the basement acts as an exceptionally effective thermal insulator, trapping the heat produced in the basement and maintaining elevated temperatures in the deep parts of the geological system beneath the plateau. Geoscience Australia's surveys of the region's heat flow, combined with deep drill hole temperature measurements conducted at sites in the broader Sydney Basin, have confirmed that the geothermal gradient beneath the Blue Mountains is higher than the average for stable continental crust. The deep rock beneath this plateau is warmer than it should be for a region with no active volcanism and no obvious recent geological disturbance. And that warmth reaches the surface. Not as volcanic hot springs or geysers. As a subtle but measurable contribution to the thermal environment of the deepest canyon systems. The canyon floors of the Blue Mountains are measurably warmer than the plateau above them. This temperature difference is partly the result of the simple physics of a sheltered valley receiving less wind and radiating heat differently from an exposed plateau surface. But it is also partly the result of the geothermal contribution from the deep basement, the slow upwelling of heat-modified groundwater through the fractured sandstone and basement rock, emerging at springs and seeps in the canyon floors and contributing to a microclimate that is more thermally stable across seasons than the surface above. This thermal stability is the key to the most significant biological discovery made in this landscape. In August of 1994, a national parks officer named David Noble was descending by rope into a remote canyon in the Wollemi Wilderness section of the Blue Mountains National Park. The Wollemi Wilderness occupies the northern and northwestern part of the park, a section that is among the most physically inaccessible terrain in southeastern Australia. Noble was an experienced bushwalker who knew this country well. He was descending into a canyon system that was off any marked trail and required technical rope equipment to access. At the bottom of the canyon, he found trees he did not recognize. He collected samples. He photographed what he could. He brought the samples back to the Royal Botanic Garden in Sydney. The botanists who examined the samples were, by their own accounts in the years afterward, initially unable to accept what the material was telling them. The trees were Wollemia nobilis, a species belonging to a genus that existed in the fossil record and had been declared extinct approximately 2 million years ago. It had been extinct, according to every biological record available before that August afternoon in 1994, for 2 million years. Except that it had not been extinct. It had been growing in a canyon in the Wollemi Wilderness, accessible to any person who had the technical skills to descend into that specific gorge, throughout the entire period that science had been categorically certain no such thing existed anywhere on Earth. The Wollemi Pine, as it came to be known in the public coverage that followed the announcement of the discovery, is a coniferous tree related to the Kauri and Araucaria families. It can grow to over 40 meters tall. The specimens Noble found in the canyon ranged from young trees to mature adults that were clearly many decades old. The canyon contained a viable population, small but apparently self-sustaining, that had been reproducing and persisting through the climate changes and ecological transformations of the last 2 million years in complete isolation from the knowledge of science. The population was small. Fewer than 100 individual trees in the original discovery location. That population, maintained over 2 million years of climate variation, presents a puzzle that researchers have not fully resolved. The genetic analysis of the Wollemi pine population showed that the surviving trees are essentially clonal. They are genetically almost identical to each other. This near-zero genetic variation should, according to standard population biology, make the species extremely vulnerable. A genetically uniform population has no variation to draw on when conditions change. Disease, drought, any environmental stress that the current genotype cannot tolerate should be capable of eliminating it. Yet the population has been stable for 2 million years. The researchers who have studied this genetic paradox most closely describe it in their published work as presenting a significant challenge to standard models of population viability. The explanation for how a genetically uniform population of fewer than 100 trees has maintained itself through 2 million years of environmental change without collapsing is not established. What is established is that the thermal stability of the canyon floor environment is a contributing factor in the population's survival. The geothermally buffered microclimate of the deep Wollemi Canyon maintains conditions that are more stable across both seasonal and longer climate cycles than the conditions on the plateau above. The canyon's physical shelter combined with its thermal stability has created a refugium, a space where conditions favorable to the Wollemi pine have persisted through climate shifts that eliminated conditions for most vegetation communities in the surrounding landscape. The Wollemi pine survived because it found a place where the deep earth was keeping the canyon warm enough, through enough climate cycles, for long enough. It is almost certainly not the only thing that did. The biological survey of the deep canyon systems of the Blue Mountains and the Wollemi Wilderness is incomplete. The terrain is physically inaccessible by standard field methods across large areas. The kind of comprehensive biological inventory that would reveal whether other species have been persisting in similar refugia in unsurveyed canyon systems has not been conducted. What the surveys that have been conducted show is a consistent pattern of higher biological diversity in the canyon floors relative to the plateau above, with species assemblages in some cases suggesting long isolation from comparable populations elsewhere in eastern Australia. Each survey that has penetrated further into the most inaccessible sections of the canyon system has produced species either not previously recorded in the region or not previously known to science. The pattern of discovery has not yet reached a point where the next survey is likely to produce nothing new. What else is in those canyons, waiting for the next person who descends into the right gorge, is not currently known. Now let us talk about the water. Because the hydrology of the Blue Mountains is where the geothermal and geological systems connect to the biological systems in ways that have been documented but not adequately synthesized. The Blue Mountains form the western boundary of the catchment that supplies drinking water to approximately 4 million people in the Greater Sydney region. The Warragamba Dam, which sits at the foot of the escarpment, collects the water that drains from the plateau. The quality and reliability of that water supply depend entirely on the ecological integrity of the catchment above it. The water that moves through this catchment is not simply rainwater running off the surface. It includes a component of deep groundwater that has been circulating through the fractured sandstone and basement rock for extended periods before emerging at springs and seeps in the canyon systems. Isotopic analysis of water sampled from springs within the deep canyon systems has revealed residence times measured in decades to centuries for some of the deep circulating water, indicating that part of what emerges in the canyon floors has been underground since before the European settlement of the Sydney region. This deep water circulation is driven in part by the geothermal gradient. The elevated heat flow from the radioactive basement drives upward movement of groundwater through the fracture systems in the sandstone, carrying the thermal signature of the deep basement to the surface in the canyon floor spring systems. The spring ecosystems of the Blue Mountains canyon systems, the small wetlands and seeps that are fed by this deep groundwater, are among the most biologically sensitive and least studied environments in the park. The specific chemistry of the deep groundwater, modified by its passage through the basement rock and carrying dissolved minerals that reflect that passage, creates conditions in the spring ecosystems that are distinct from conditions in the surface-fed waterways. Species adapted to those conditions in some canyon floor springs have no equivalent populations in the surrounding landscape. Those species, like the Wollemi Pine, are maintained by the steady output of deep groundwater from a system that has been functioning continuously for longer than most of the human history of this region. Now let us talk about the people. Because the human history of the Blue Mountains is deeper and more continuous than the European pastoral and tourism history that occupies most of the public narrative about this place. The Darug, Gundungra, and Wiradjuri peoples have traditional connections to different parts of the Blue Mountains. Their country encompasses the escarpment, the canyon systems, the plateau, and the rivers that drain it in all directions. Their relationship with this landscape is not the relationship of people who arrived in a place. It is the relationship of people whose identity, knowledge, and cultural practice are constituted by and inseparable from the specific features of the country they have always inhabited. The archaeological record of human presence in the Blue Mountains has been the subject of systematic research that has extended and deepened through improvements in dating technology and survey methodology over the last 30 years. Rock shelters in the Blue Mountains have yielded stratified deposits of cultural material that document human presence at specific locations across time spans reaching back well beyond 10,000 years at multiple sites. Optically stimulated luminescence dating of the sediment sequences in those deposits has produced dates for the deepest cultural material in the best preserved sites that extend toward the period of initial human colonization of the continent. The Blue Mountains were not peripheral country in the history of Aboriginal southeastern Australia. They were part of the landscape traversed and used from the earliest period of human presence in the region. The cliff face engravings and rock shelter paintings found at sites across the escarpment and plateau document a tradition of marking and understanding this landscape that extends across the full span of human presence here. The Wollemi Wilderness, the section of the park where David Noble descended into the canyon in 1994, is within Wiradjuri traditional country. The knowledge systems of the Wiradjuri encode detailed information about the landscape of the high country and the deep canyons, including knowledge of specific locations and resources that the physical inaccessibility of the terrain does not make available to casual observation. Whether traditional knowledge of the Wollemi Wilderness ever encoded specific awareness of the unusual trees in the canyon system where Noble made his discovery is a question that the research literature does not address directly. What is established is that the traditional knowledge systems of the peoples whose country includes the Blue Mountains contain detailed ecological and geographical knowledge of the canyon systems that Western scientific survey is still in the process of matching. This is the consistent finding everywhere in Australia where the comparison has been genuinely made. Now let us bring the full picture together. The Blue Mountains are a geological system whose visible surface, spectacular as it is, represents only the outermost layer of a structure that extends from the surface through 300 million years of sedimentary rock to an ancient crystalline basement that is producing heat and driving fluid movement through the entire column above it. A biological archive in the deep canyon systems whose contents are still being revealed, including at least one species that survived 2 million years of extinction in a geothermally stabilized refugium that science only discovered in 1994. A water system that supplies 4 million people and is fed in part by ancient groundwater that has been circulating through the deep rock for centuries before emerging at the surface. And a human history extending back to the founding of this continent's human story, maintained in knowledge systems that contain accurate information about this landscape in depths of detail that scientific survey is still working to match. None of this is adequately communicated at Echo Point. None of it is on the scenic railway. The people who visit the Blue Mountains on a day trip from Sydney are experiencing the surface of one of the most scientifically significant and biologically extraordinary landscapes in Australia. The surface is worth the drive. What is beneath it is worth far more than most visitors imagine while they are standing at the cliff edge taking photographs. And in the deep canyons of the Wollemi Wilderness, in the gorges that are accessible only to those with the equipment and knowledge to descend into them, whatever the next David Noble finds when they reach the canyon floor is still waiting to be discovered. If this changed how you think about the Blue Mountains, leave a comment below and subscribe for more Australian history and science that most people were never properly taught.